Welcome back. We're now going to be looking at Chapter 20. And in Chapter 20, we're going to be analyzing circuits and the connections that we can put resistors in order to transmit electrical energy from where we have it to where we need it, and how those different connections will do different things to our current, our voltage. So we're going to be investigating circuits and circuit elements in this chapter. And we're going to start off by talking about schematic diagrams. Now, as you've probably noticed, you've watched me draw these things, and I've drawn this as my battery and said, hey, I've actually listed this out and actually written out battery on it. And you saw it was really, really ugly. Well, this got old really, really fast. And so what they did was they came up with a set of symbols to represent like batteries and resistors and such. This one that I'm drawing right here, this is our symbol for the battery. And so the long line is considered to be the positive connection, so that'll be on this side, and then the negative is going to be the short line, so that would be that side. But we would draw this symbol representing the battery rather than actually drawing a battery out. Okay, and you will find all these symbols that you have to use on your reference table. So tomorrow we will get practice in drawing these, and again, they don't have to be beautiful, but it just makes your life easier in drawing it rather than drawing an actual lamp or a resistor or a generator or a capacitor or something like that, or an ammeter, voltmeter, all those. You can use these symbols in place of that. So we'll practice with this tomorrow. Now, we are going to talk about electric circuits in this chapter. An electric circuit is a way that we can transport the electrical energy from where we have it, the battery, the generator, to where we need it. The resistor, the lamp, the ammeter, voltmeter, whatever we want. And so the electric circuit is that pathway that is created to transport that energy. Yep. Now, a couple definitions. A load, by definition, is any device, the electric circuit, that will dissipate or give off that energy. And in general, that'll be like a resistor. But it could be other things as well. It could be an electric motor, which, again, you can argue is a resistor and stuff like that. But probably the one we're going to use is like a resistor, is that load. A closed circuit is one in which the charges will actually flow. Okay, and then there are no breaks in that path. An open circuit has that break, and so charges cannot flow. Okay, so in order to be a working circuit, you have to have that closed loop. Okay, that's one of the things. In order to have a working circuit, you have to have that closed loop. Okay. Also, there must be a source of energy. Okay, so this is where we use this as our battery or our generator, or some batteries is one we're going to primarily use. But it has to be some source of energy to get those charges to move from one spot to the other. There has to be a voltage source there. And really, those are the only two things you have to have in order to have a working circuit. The easiest one you could ever do is if you take that 9-volt battery, we mentioned this before, and you lick it. That is a working circuit. You have your energy source, the 9-volt battery, and you have the closed loop. By closing it with your tongue, charges will flow through there. Okay. Now, real quick, I'm going to talk about EMF. EMF is another way to kind of describe that energy that we need to move those charges. It's called electromotive force. It's really just another way of saying voltage, okay? But it refers to the entire voltage of the entire circuit. It's the energy to move the charges not only through our circuit, but also inside our voltage source as well. So we will talk about this briefly, but just know that really, for our purposes here, EMF is basically the same thing as voltage. Okay? It gets a little more complicated, and if you go to the higher levels of physics, they're not the same thing. Okay, and we'll discuss how later on, actually tomorrow. But for our purposes, basically you can think of EMF as voltage. The symbol for EMF is a scripty E that looks like this. Okay, so if you ever see that, that's kind of what we're referring to. The terminal voltage is the voltage on the outside. So remember how we said the EMF is the energy per charge for the entire thing, including what's inside the battery? The terminal voltage is what's on the outside. So if I have my battery, and I'm going to hook that up to a lamp, like this, okay? The EMF refers to the energy of the entire thing. The terminal voltage is just what's running the lamp. So terminal voltage is what runs the lamp. Whereas the EMF is the total energy per charge in the entire circuit. So there's subtle differences, and really for our purposes, we're not going to have to discern between the two, but I wanted you to know that if you ever hear these terms, EMF, terminal voltage, they do refer to slightly different things. All right, now there are two types of connections in a circuit, and we're going to spend the rest of our time in this lesson learning about the first one called series. And a series circuit is when all devices operate on the exact same line. Okay, and I'm going to do this picture. And what I'm going to do is I'm going to put 3 resistors all in series. And I'm actually going to put an ammeter in here too. Oops. I'm actually going to change color for my ammeter. I'm going to put an ammeter in here that's in series with the whole thing to measure the total current. But in this, the devices are all hooked up one after another after another. So here's our R1, here's our resistance 2, here's our resistance 3. And this down here, this is, I'm going to put this in purple, our total voltage. Okay, and so what's going to happen is the current is going to come out. Leaves my battery, it's going to come up. It has to go through R1, has to go through R2, has to go through R3, has to come back around here and go through my ammeter. That's my I total. Okay. Now, in all of the subsequent slides, I'm going to be referring back to this diagram. So make sure you have this diagram written down before we go any further. So all these devices are one after another after another. So if there's any break in this path, then we have an open circuit and this thing won't work. Okay, so if there's any break, if I come along and I cut the wire between R2 and R3, then they all go out. There cannot be a current flow because then we will have an open circuit. So keep that in mind. That's the thing with series. They have to be one after another after another. Now, there are 5 major characteristics, okay, that we're going to discuss. Out of these, three of the equations I'm going to give you are labeled in your reference table under series circuit. The other 2 are actually just Ohm's law, and we'll come back and take a look at that. But in the first one, since the charges must follow the same path, whatever current leaves the battery has to go through each of the subsequent resistors. And so if we go back to my diagram here, I said that that's I total, that current leaves here. Well, we have I1, that's the current that goes through R1. I2, that's the current that goes through R2. I3, that's the current that goes through resistor 3. I can't write a 3 there. There we go. But that, because it's all in the same path, they all have to be equal to each other. And so if we go back to this slide, our formula is going to be that I total equals I1, which equals I2, equals I2, which equals I3, which equals anything else that we have. If I had 10 resistors in series, then all the currents would be the same. I1 equals I2 equals I5 equals I10. They all have to be the same. So that's the first one. The second one is that the current is resisted by each of the resistors in turn. And so, in essence, the total resistance must be equal to the sum of them. So if I go back and I look at my diagram that I drew, I come back to here. Every time I add a resistor in series, I am in essence making my total resistor longer. And remember, when we did this in our lab, we showed that as the length of the resistor goes up, the total resistance goes up. And so we can write this as R total, and I'm going to put this in green. The total resistance when in series is equal to the sum of the resistors. And this is based off of that the resistance is proportional to the length. of our resistor. I should go back up here too as well, and I forgot to put this in, so come back to this. This total current, this is based on the law of conservation of charge, because the total amount of charge has to remain constant. Okay? And so whatever leaves has to go through all of them. Okay? Now, the third characteristic states that the total, it's just Ohm's law, that if you want to find out the current that's flowing through the whole thing, and actually let me change colors here. I'm going to put this in orange. That the I total has to equal V total over R total. So if I want to find out what the total current flowing through that circuit is, I'm just going to take the total voltage of my circuit and divide it by my total resistance. So this is just Ohm's law. Okay, and I'm going to put that in, keep that in orange. This is just from Ohm's law. Now, the fourth one, I need to scroll this up just a touch. The fourth one is that the total potential difference is divided up over each of them, okay? Over each of the resistors, such that if you add up the individual voltages, you have to equal the total voltage. And let me scroll back up to the diagram so I can tell you what I'm talking about. So here's our diagram. We know that we have a total voltage down here. That's the total energy provided to our circuit. Well, if I were to take a voltmeter and measure the voltage across just R1, so that's how much energy it takes to get through R1. And if I were to take another voltmeter and measure it, so it's just across R2, so that's going to measure the energy it takes to get through R2. And then I put another one here to measure the third one, that the total voltage provided has to be equal to the sum of the individuals. And you can kind of think of this as a law of conservation of energy. When my charges go through my battery, they gain energy. As they go through the resistors, they lose that energy. And so it's kind of like a roller coaster. And we'll go through with more examples of that in our class tomorrow. But let me draw this one out, or give you the equation. So the total voltage, V total, must equal V1 plus V2 plus V3 plus dot, dot, dot. Okay? And again, that's based off of law of conservation of energy, the total amount of energy in a process. Now, the last characteristic is just applying Ohm's law to each one of those individually. So if I want to find out and I'll put this in blue pencil, if I want to find out what the V1 is, I would just take whatever current flows to the first one times the resistance to the first one, and that'll give me the energy or the voltage drop across that first one. If I want to find V2, I'll just take I2 times R2. Now remember, I1 equals I2 equals I3 equals I total. So in essence, I could actually even write this as I total times the individual resistances, and that'll give you my voltage drop. So again, this is just from Ohm's law. Okay. We're going to apply these. Okay. Now, we're gonna do a lot of practice with these tomorrow, but let me even leave you with this one very key bit of information. Really, really important while doing these. It is crucial that when you are doing problems like this, and you're using Ohm's law, like this one, that you keep your subscripts the same. You can't find V2 if you use I1 and R3. If I want to find V2, I have to use I2 and R2. Okay? If I want to find I total, I can't use V1 and R2. If I want to find I total, I have to use V total over R total. Very, very important to keep the subscripts the same. Guarantee that's a quiz question tomorrow. All right, so we will practice these tomorrow when I see you in class or online. So everybody have a fantastic day. We'll see you later. Bye.